All right, so as always, you may wish to pause the recording at this point in order to read the problem statement and come up with your own method for a solution. Okay, so in this problem, we've been asked to do many things. We've got a mixture of oxygen, nitrogen, and argon in the proportions that best approximates what dry air might look like. We're going to skip over part D. We're not going to do that. You can verify that the analysis we do in parts A through C gives you virtually the same numbers if you just use the air tables anyway. So this illustration is just to give us some practice dealing with mixtures of ideal gases. So the first thing we're asked to do is to find the apparent molar mass of this mix of gases and also the ideal gas constant for this mix of gases. In order to do that, I'm going to first find a mass analysis of this mixture. I've been given a volumetric analysis, which is the same as a molar analysis. So to find the mass analysis, I'm going to basically set up a table and use the fact that I have the molar analysis and the molar mass of each individual species to come up with the masses. The easiest way to do this is to assume that you've got 1 kilomole of mixture. I don't actually know how many moles I have just yet, but I'm just going to pretend for right now that I have 1 kilomole of mixture. The convenience of doing that is in the fact that the mole fractions now become the number of moles of each species. For instance, I have 21% oxygen by mole fraction, so if I have 1 kilomole worth of mixture, that means I have 0.21 moles of oxygen, and so on for nitrogen and argon. Oxygen, nitrogen, argon's molar masses are looked up next in the periodic table. I'll just list those there for you in kilograms per kilomole. And now I'm going to take the number of moles and multiply it by the molar mass of each individual species, and that will give me the mass of each one of those species, assuming that I have 1 kilomole of mixture. So for instance, 0.21 times 32 gives me 6.72 kilograms of oxygen in 1 kilomole of mixture. And I add up that column and get 28.97 kilograms of mixture. So that is the mass of this mixture, assuming that I have 1 kilomole, which is very convenient because if I have 1 kilomole and that's its mass, that number is also the molar mass of the mixture. So that's the first thing I've been asked to find, is what the molar mass of the mixture is. Okay? So there's the first part of part A. Now, we don't actually need the mass fractions for the rest of this problem. Okay? But since we're almost there, let's spend just a few extra seconds reminding ourselves how to go all the way to the mass analysis. So if I didn't want a full mass analysis for some reason, I could do that by taking the mass of each individual species dividing by the mass of the mix. For instance, 6.72 kilograms worth of O2 divided by 28.97 kilograms of mixture gives me 0.232 mass fraction for the O2. Likewise for the N2 and the argon, and when you add those guys up, it should equal 1, and in fact it does. Okay, so we don't actually need that mass analysis per se in this problem. All I needed really was the molar mass of the mix, but it's a good reminder to myself how to do that. So there's the first part of part A. There's the molar mass of the mixture. To find the ideal gas constant, all I have to do is divide the universal gas constant, which is in a molar basis, by the molar mass of the mix. So 8.314 divided by 28.97 gives me the familiar 0.287 kilojoules per kilogram Kelvin for this mix of gases. Moving right along, I'd like to find the mass of the air. Now you might think that I've already found the mass of the air. You might say, oh, that's 28.97, I already got that. That was assuming that I had 1 kilomole. I don't have 1 kilomole. So the way I'm going to find the mass of the air is by appealing to the ideal gas equation using the fact that I know the pressure, volume, and temperature. So I'm going to solve that guy for mass, and I'm going to use the values of pressure, volume, and temperature given, and my newfound value of R for this mixture, 0.287 kilojoules per kilogram Kelvin, use the appropriate unit conversions and find the mass. Don't forget, ideal gas equation requires absolute temperature. That must be in kelvins. You cannot plug in 27 degrees and have this work. So finally the mass is 1.161 kilograms. Moving right along, we'd like to find the heat transfer to the air during this process and also the entropy change. Now for the moment, if you just forget that you know anything about mixtures of ideal gases, and we saw that you had a closed system undergoing a constant volume process from one temperature to the next, and also assuming that it is an ideal gas, you'd be able to do this problem without much trouble. You'd identify your system as being the air inside your rigid tank. You'd identify that there was heat transfer going in. You'd write the closed system finite time version of conservation of energy, ignoring kinetic and potential energies. Recognize that there's no work, there's no paddle wheels, you're not plugging it in. It's constant volume, so PdV, work, is 0. And you'd solve it for Q. So Q is mass times the change in internal energy, or specific internal energy. So the new part of this problem doesn't come until I get here and go, how in the world do I find U2 minus U1 when my stuff is oxygen and nitrogen and argon all mixed up? So the link between this and what we're doing now is the property relations themselves. So a change in specific internal energy for the mixture can be found by taking the change in internal energy for each individual component, multiplying it by its respective mass fraction, and adding all of those guys up. Now I run into a problem if I try to do this because I don't have tables for oxygen, nitrogen, and argon by themselves on a mass basis. I have them on a molar basis. But that's not a big deal because m times little u gives you big U. So does n times little u with a bar. So if I take the number of moles and multiply it by a molar specific property, I still get the big property. Or in mole fraction form, the change in internal energy on a molar basis for the mix is the sum of the individual mole fractions times the difference in specific internal energies for each individual component on a molar basis. So what I'm going to do is I'm going to look up O2, N2, and argon's internal energy changes per unit mole, multiplying by the mole fraction, and add them all together. Let's look at O2 to start with. U2 minus U1 with a bar on top is 10,614 minus 6,242. Where did I get those numbers? Both of those are table lookups in your property tables. So you should go find them and verify that those numbers are correct. Those are on a molar basis. So that is 4,372 kilojoules per kilomole change in internal energy for O2. Nitrogen is done exactly the same way using the nitrogen tables. And then I get to argon and I go look at my tables and I get stuck. Okay? So if you're following along in your tables and you look for the argon tables, you'd find that there ain't any. Why is that? Well, argon, like helium and all those other things in the far right-hand side of the periodic table, are noble gases. Noble gases are so close to ideal gas behavior that if you model them as having constant specific heats, it's fine. Always. Always, always, always. That's why there are no tables. The constant specific heat model is perfect for them. So that means I can get away with a little less work for argon. I can multiply C sub V times delta T to get delta U. Now this is C sub V bar. This is the specific heat for argon on a molar basis. So the cool thing about that is on a molar basis it's the same for argon as it is for helium as it is for all of them. So I don't need the molar mass here to find C sub V on a mass basis. I only need C sub V bar, which is the same for all of them. So it'll take you a little hunting to find what that C sub V is. And we talked a little bit about that in class, but once you have it, it's the same for all of them. So you'll find that is 12.5 kilojoules per kilomole Kelvin. Multiply it by your temperature difference. There's your change in specific internal energy for argon on a molar basis. Okay, so for the mixture, I add all those guys up after I multiply them by the individual mole fractions, which were given in the problem, and I find that the change in internal energy is 4,214 kilojoules per kilomole. Now at this point, what I chose to do was go back to a mass basis because I've already calculated the mass of the mixture and I didn't want to bother calculating the number of moles in the mixture. So I can take that delta U that I just got, divide by the molar mass of the mix, which I have also calculated, and I find that the change in internal energy for the mix on a mass basis is 145.5 kilojoules per kilogram. And finally, I multiply that by mass to get the heat transfer into the system as 169 kilojoules. An alternative to doing this was to take the number of moles of the mixture and multiply it by delta U with a bar on top. You'll get exactly the same answer. In that case, you would have had to calculate the number of moles in the mixture first. So you might want to do that just to verify that you do in fact get the same answer. Okay, so we've done part C1. Now it's time to do part C2 to calculate the entropy change during the process in kilojoules per Kelvin. Notice that I asked for the entropy change. Entropy is just a property. So in this problem, I don't have to apply the accounting of entropy to this system. I can calculate the entropy change simply by taking the mass of the system and multiplying it by the specific entropy change of the same system. I might afterwards go find how much entropy was generated in this process, but I don't need the accounting of entropy to find the entropy change. So the entropy change per unit mass can be found much in the same way that the entropy change, or I'm sorry, the internal energy change per unit mass was found in the previous part of the problem. Or I can do this on a molar basis also. So there's a parallel between what I did in part C1 and what I'm doing in C2. I'm just switching the properties from little u to little s. So I'm going to take the mole fractions, multiply it by the change in specific entropy of each individual species, and add them all up. So once again, I'll do O2 into argon, add them up respectively, and see what we get. Now the entropy change of an ideal gas is a little bit more complex. Remember, it's got a temperature-dependent piece, and it has a pressure-dependent piece too. So these guys, the S supernauts, are functions of temperature. Those are my table lookups, but I have this extra piece to add on to it. So again, specific entropy is a function of temperature and pressure for an ideal gas, not just temperature. Here's something else to be aware of. I've written P of the O2 at state point 2 over P of the O2 at state point 1. Those are the partial pressures of O2. I cannot use the pressure of the entire system. Very important point. Remember that Dalton's model is what allows us to do any of these calculations. And Dalton's model says that each component of an ideal gas mixture behaves as if it existed at the temperature of the entire mixture and the volume of the entire mixture. So T of oxygen is the same as T of mix. Volume of oxygen, same as volume of mix. Not so with pressure. So in order to make this work, I have to use the partial pressures, which means I multiply the total pressure by the mole fraction of the oxygen. In this problem, if you didn't do that, you would have lucked out, because at state point 2 and state point 1, the mole fractions of oxygen are exactly the same. It hasn't changed. But that's not always true. My mixture composition can change, like in mixing problems, or in open system problems also. Okay? So important point, must use the partial pressures. I don't have P2 yet. I can find that because I know that this is a constant volume process. So I use the ideal gas equation, and I can calculate P2 as P1 times T2 over T1, which turns out to be 166.7 kilopascals. Or I can just use the fact that P2 over P1 is equal to T2 over T1, which is 500 over 300, or simply 5/3. Okay, so you can calculate P2 if you'd like. In this problem, I opted just to plug in P2 over P1 as the ratio 5/3 right here. In any case, there's my specific change, or my change in specific entropy on a molar basis for O2, 11.13 kilojoules per kilomole Kelvin. Nitrogen is handled in exactly the same way. So I'll leave it to you to verify that you should get 10.7 kilojoules per kilomole for the nitrogen. Argon, however, is handled differently. Constant specific heats here. So I can get away with writing C sub V times log T2 over T1 plus, not minus, plus universal gas constant times the logarithm the ratio of the volumes. I opted for this form for the constant specific heat argon because V2 over V1 is 1. So I used this one purely out of convenience. I could have used a C sub P value that had minus R log P2 over P1, but this is less work. Okay, so you plug in those numbers and you find that the change in entropy for argon is 6.4 kilojoules per kilomole Kelvin. Once again, I multiply those by the mole fractions, add them all up, and get delta little s for the mix on a molar basis. And as I did before, I'll take that and divide by the molar mass of the mix to find the change in entropy of the mix on a mass basis, 0.371 kilojoules per kilogram Kelvin. And finally, I multiply that by the mass of the entire mixture to find that this change in entropy for this mixture of gases is 0.742 kilojoules per Kelvin.